Right, let's train a n-gram model using KNLM in a 6-gram model. But please note that we can change this in order to change the n-gram model. We'll be naming it sapedi ngram.arpa because this is the format that KNLM produces when training a model. Right, now this is done, we convert this ARPA file into a KLM file, as this is a binary format and it is much more efficient to use when evaluating the model on different datasets. This is our script for evaluating the newly trained model on our encoded datasets. Let's run it. As you can see, a Sapedi language model with a BPE of 2000 and a 6-gram n-gram model, we can see that our perplexity score when evaluated on the encoded validate dataset is approximately 27.72. This results in a bits per character of 1.37, which we calculate via the use of the number of characters and the number of tokens. Let's show an example run of the feed-forward model. We will train this model with only 10 iterations of training on the validation dataset. This is not ideal, and this is not a tuned set of parameters, but it is quick and it's easily shown in the demo. Let's take a look. As you can see, it starts training and already goes through the first iteration of evaluating the model on the encoded validation dataset. This will get better for each iteration, as you can see here. We are now waiting for the 10 iterations to complete so that the model is then evaluated on the encoded test dataset. And this will give us our final performance metric score, which will be given in perplexity.
This project looked at the potential to use the advancements in RNA models, namely LSTMs and qRNAs, on low-resource South African languages. This was done using PyTorch and the open-source libraries made available by the AWD LSTM team, who made one of the variants that were used in this project. Due to the old version of PyTorch being used, only certain GPUs, specifically the K80 or P100s available on Colab, have unofficial support for the libraries required, although the V100 GPUs available on the UCT CHPC cluster thankfully also work well. The user then clones the GitHub repository, installs the dependencies, and only installs the qRNA dependencies if they are needed, as they are particularly large. The user can then run a simple fetch data script, which automatically collects, cleans, and splits up the data into its validation, training, and test sets through a combination of bash scripts and Python utilities. Here we are running a very small model, showing that the code runs in this environment, although the models used in this project were significantly larger and took approximately 12 hours to run. In fact, the final training of the models all took place on the CHPC, where multiple jobs could be queued up, and each job ran far faster. In total, over 200 hours of model training was performed like this on the CHPC. Once the models are run, we can head their outputs and the results and inspect them compared to the other models that we have saved using TensorBoard. We can then look at the graphs of the scalars we may have been plotting, such as our loss metrics, any text that we may have saved. Here we save the model structure and the parameters in case anything goes wrong. Or we can use the hparams plugin to visually inspect our different parameter tuning experiments. Specifically, there is an hparams parallel coordinate view, which allows for a visual comparison of the different experiments, where the user can select a specific dataset, model, and parameter ranges, changing between them at will in a nice-to-use and easily comparable visual context. Using this, we were able to determine the best choice of parameters for each of the models for each of the datasets during the project's testing phase.
This training script contains the entire configuration for one training run. All modifications that were made to the GPT-2 model can be enabled or disabled as parameters in this script. This means that any of the models in our report can be reproduced by simply putting the desired parameters in here. Let's run this example script, which trains a tiny model for 10 training steps. A new tokenizer is trained, and each of the datasets that were specified in the training example script are tokenized, and all of this is saved to a cache directory in the project. Now the training has started and we can see loss values being periodically logged to the console. The model is also periodically evaluated on the validation set. This lets us keep an eye on whether the model is overfitting the training data as the training progresses. We're at the end now, since we only scheduled 10 steps of training. One final evaluation on the validation set is being performed, as well as an evaluation on the test set. Now that the training script is finished, let's take a look at what happened. For each experiment, we log the results as a single line in the experiment logs file. Each line contains a Python dictionary with the hyperparameters used in that experiment, as well as the resulting BPC values on the validation and test sets. We use another script to convert this logs file into a CSV file containing the results of all the experiments. This is what the results CSV looked like in the actual experiments, with the BPC values of each experiment shown on the right.